Modern timber bridges. This was the theme of a nationwide timber bridge conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. Under the general heading of timber preservative treatments, the design aspect was addressed by David A. Webb from Koppers Company.
The subject which I'd like to discuss today is the preservative treatments that are used in the design of timber bridges. We are essentially talking about the pressure-treated chemicals that are used to impregnate non-durable wood timbers. These timbers would consist of hardwood and softwood species, softwood species being Douglas fir, southern yellow pine. Hardwoods would be those species which are indigenous to a specific locale, but would include maples, oaks, etc. These timbers are treated according to the AWPA, the American Wood Preservers Standards. These standards are found in the Book of Standards of the AWPA under the specifications, the commodity specs, the C3s, C2, C4 standards. There are also other federal and state regulations, specifications which deal with wood preservatives, the ASTM, the AREA, and various government specs. The three basic wood preservatives which we are talking about are creosote and its solutions with coal tar and petroleum, pentachlorophenol and oil, and the waterborne arsenicals, which include CCA, copper, chrome, and arsenic, and ACA, which is ammoniacal copper arsenate. There are no specific regulations which govern the use of treated wood. There are, however, regulations which govern the application of the preservatives to the treated wood. These application areas will not be discussed because they primarily focus within the pressure treating plants. There are some alternative preservative systems which may be used. These can be used in field cut areas, but they are not used in terms of pressure treatment. These alternative preservatives would include copper naphthenate, TBTO, tributyl tin oxide. I should also like to point out that as a settlement within the RPAR system, the rebuttable presumption against re-registration of the preservatives, that there was a consumer awareness program which cited various types of protective clothing that should be used. And this is important for individuals who are installing or using pressure-treated wood. As a brief summary in terms of reflecting on the types and the end uses with respect to treated wood, both hardwoods and softwoods, in the timber bridge area, it is important to point out that oil-borne preservatives give the maximum protection with regard to weather resistance. This is both creosote and oil in penta. And these preservative products should be used for hardwoods and softwoods. It is further recommended that with respect to softwood materials that the waterborne arsenicals could be used, but the waterborne arsenicals should not be used in the pressure treating of hardwoods. Laminated structures is another area for consideration. Laminates may be constructed using both hardwoods and softwoods. However, normally softwoods such as Douglas fir and southern yellow pine are the species which are used in laminating. The glue or adhesive that is used in laminating must be phenol resorcinol or resorcinol type adhesive systems. Treatment with oil-borne preservatives, creosote or pentachlorophenol, should always be performed after the gluing or the laminating occurs. It is not satisfactory to laminate waterborne treated material after the treatment has occurred. There are problems with the adhesive systems in adequately adhering to the treated waterborne products. In summary, I would like to comment that the benefits of preservative-treated wood in the use of designing timber bridges are a very important, significant factor, and they have the possibility of enhancing the use of preservatives and timber in timber bridges.
We have looked at general concepts and uses for timber bridges, as well as talked about the design of timber bridges. The key to success begins with the treatment of the timber itself. So let's start there, the arrival of the raw wood. While many types of timber have been used for bridge construction, this firm, Wheeler Consolidated, St. Louis Park, Minnesota, prefers Western Douglas fir. Timber is unloaded and a treatment process begins. First, the wood is incised to give a pathway for the treatment material, and then trimming begins to occur. Notice that all of this work is done prior to any chemical treatment of the wood. The wood is well peeled, and all machining is completed before the actual treatment process. Machining to include incising to improve the preservative penetration, as well as the operation of cutting, framing, or drilling of holes. The wood is then loaded on a tramway, capable of carrying 3,400 board feet, and taken into the treatment cylinder. While it's in the cylinder, the technician uses the control panels to check the treatment procedure. The wood is taken out of the cylinder. In good treating plant operations, easily treated woods and resistant woods are not included in the same package. The easily treated wood under such conditions would absorb more than the average, and the resistant material would absorb less, so the types of wood are not mixed. Test borings are done to measure the treatment penetration. Actually, much of the testing and review of the treatment procedure is done in a lab. Now the treated wood is prepared for assembly. Shipping rods are threaded through the pieces, pre-drilled and pre-formed. The rods are tightened and stressed. This stressing procedure is much the same as you will see in the actual erection of this post-stress bridge. The stressing is sufficient to keep the bridge pieces from separating. The loaded deck is then shipped to the bridge site. Modern Timber Bridges. This was the theme of a nationwide timber bridge conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. Maintenance and life of timber bridges, a subject of a talk by Frank W. Muchmore from the United States Department of Agriculture Forest Service.
I'd like to discuss the role that maintenance plays in assuring long life for timber bridges. First, a little background material. Wood is a marvelously adaptable structural building material. When it's treated with a compatible preservative to prevent early decay deterioration, it can certainly be an economical, practical, and long-lasting structural material, and it's particularly adaptable to short-span bridges. Structural wood has many advantages. First, it's simple to fabricate. It's lightweight and easy to install. It has a high strength-to-weight ratio. It does have excellent sound and thermal insulation properties. Has good shock resistance. For example, the AASHTO bridge specifications don't require impact loading for timber members used in bridges. It has good fire resistance. Large structural members, when they are subjected to flame, they develop a char layer that effectively insulates the wood and slows the burning rate, so that a high percentage of structural strength is maintained for considerable periods of time under fire conditions. Wood is totally immune to commonly used de-icing chemicals. It has unique aesthetic properties and qualities. It is a renewable resource. It's one of our few building materials that you can farm and get crop after crop. It is economical, and it's long-lasting when it's properly treated and protected. Some of these properties, its inertness to de-icing chemicals, and as well as some new design developments such as glued laminated deck panels and pre-stressed laminated decks, make it more desirable than ever to use in highway structures. Another area that can add to the lifespan of timber structures is attention to design details in the design phase of timber bridge construction. Some of the things to pay attention to, that designers need to pay attention to, are to use only wood species that are readily and effectively pressure treated. For exterior use, oil-borne pressure treatments are more effective than water-borne treatments. All wood should be completely fabricated before it's pressure treated. Avoid design details that trap water and dirt and other debris. Avoid the use of boxed heart wood members to minimize the development of checks and splits in the wood. When it's practical, use glued laminated members. Avoid using roll roofing or sheet metal caps on stringers, pile, or post tops. And as much as possible, make bridge decks an impervious roof over the stringers. I think one of the most important factors in assuring long life for timber bridges is an effective inspection and maintenance program. If we have thorough, periodically scheduled inspections by qualified inspectors, this is the key to an effective maintenance program, and we can significantly prolong the useful life of timber highway bridges. Timber bridge maintenance can be divided into three categories. The first is preventive maintenance. In this area, decay has not yet started, but conditions which are conducive to decay are present. Moisture control and some in-place preservative treatments are probably the most effective maintenance measures for preventive maintenance. The next category is early remedial maintenance. In this situation, decay is present in the wood, but if corrective measures such as in-place treatment and perhaps replacement of some of the minor members such as curbs and railing members are done, the structure will be able to remain in service for many years to come. And then the third category is major maintenance, major rehabilitation or replacement. Unfortunately, most timber bridge maintenance is ignored until it reaches this stage. In many cases, replacement of most of the timber members is necessary if it goes to this stage. Okay, in summary, wood is good if timber bridges are properly designed, constructed, and most important, properly maintained.
Okay, as discussed, my topic today is wearing surfaces of timber bridges. We use many wearing surfaces for timber bridges. The purpose of the wearing surface is to save the timber from structural wear. The different materials that we use are aggregate, native soil, timber running planks, full-width running planks, steel running plates, actual laminated decking, asphalt, such as asphalt pavements or chip seals, and other innovative types. All of the above wearing surface treatments are effective depending on the traffic types and the maintenance that is used to treat the bridge. This paper discusses existing timber bridge wearing surfaces throughout the nation and Alaska and discusses trends and coming attractions. The typical timber bridge is flexible and, like other bridges, typically has joints. It is the joints that cause problems in cracking, pulled nails, loosened bolts, interlaminate wear, and surface wear on any bridge wearing surface, whether the native material for the bridge is timber, concrete, or steel. I'd like to discuss each type of wearing surface separately, including preferred applications and their strengths and weaknesses. As you'll see in the paper, there are schematics and photos of in-place bridges illustrating the use of different materials and the relationship between the deck and the wearing surface. I'd like to start with the aggregate or native soil surfaces, in that it's the one that's been used historically most. Native soil and aggregate are very easy to apply and very inexpensive, except the problem comes with moisture and the collection of moisture on the bridge deck and the wearing of the timber bridge because of the aggregate that abrades the wearing surface. The moisture also is a problem with timber deck, and even though it's inexpensive, there are some maintenance problems, and probably you lose some life of that bridge. The timber decking for running planks is very inexpensive also, but the life of it is somewhat limited. You might get 5 to 10 years of life on running planks. If you only use the running planks that are maybe 3 or 4 planks wide, you end up with possible maintenance problems in between the running planks and some wear in the decking at that level. That's why in our Region 1 in the Forest Service and in other places you'll put the running planks, the timber running planks, the full width of the bridge, and therefore you avoid the wear in between the planks because you've got a full width. There is some moisture problems with this type of running planks because it does collect between the planks and the actual deck. Also, you have some problems that the nails that you use to tie the planks to the deck cause holes that moisture can get into and wear the surface from moisture getting in, and also bacteria and fungi that do eat on the timber. If you've got a treated timber deck, if you put the running planks on, you break through that treated layer and possibly moisture and fungi can get on into the center of the wood that is not treated. The next type are these steel running plates, which have many of the problems that the timber has. Some of them last long, but many times the steel running plates will get torn up by snow plows or other type of maintenance equipment. We typically don't use the steel running plates anymore in that they do become a maintenance problem, even though structurally they're very sound. After the steel running plates, many times the actual laminated deck is used and no running surface is put on it or wearing surface is put on at all, in that if the traffic is low, structurally it's sound, and if there's not too much traffic, you don't have a problem. It's the excessive traffic and maybe aggregate and different other abrading items that get on a wearing surface that will wear the deck. But if the traffic is low, you can get by without the running planks or plates. Usually when you get into larger traffic volumes, you'll end up trying to use the asphalt wearing surface. We have a problem with many timber decks. The joints are the problem, so you do need a very solid timber deck to avoid cracking and propagation of cracks from joints through the asphalt wearing surface. If we talk about the types of bridges that we're putting in now from decks, the old nail laminated decks used to have quite a bit of delamination, and so you had a joint between each lamination, and many of those would cause alligator cracking in the asphalt, and the wearing surface would break up, and you might not get more than 5 years of life from it. The glue laminated decks, where you had 4-foot wide panels, reduced that cracking, and the only places we normally would see cracks then are between the joints of the planks. We have gone further with that and have used dowels, which sometimes helps reduce that propagation of the crack between the glue laminates. Beyond that, in the recent past, in the last 5-10 years, we've used some geotextiles between the decking and the asphalt wearing surface, which reduces the propagation of those cracks. We've had some bridges in over 5 years with no measurable cracking because of the propagation. A couple of the brand names are Petrotech and Repave. Both seem to be effective. With the new stress timber decks that are coming out now, there are no joints in the deck, and maybe even a chip seal will afford a wearing surface that's adequate, especially on lower trafficked roads. On these asphalt wearing surfaces where we go beyond the chip seal or the double penetration treatment, we use 1.5 to 3 inch wearing surface that'll give you a 10-year life at least, similar to an asphalt road surface. Some we've gone as much as 20 years. The Ontario government in Canada has had some 10-year life bridges that are stress decks that are still working effectively with the asphalt wearing surfaces. That pretty much covers the types of wearing surface that we have on the timber bridges. In summary, we have many varied wearing surfaces that do work, and the economics depend on the traffic that's utilizing that bridge. I think that for many existing bridges, you can go through and put new wearing surfaces on them effectively, whether it be planks, plates, or asphalt wearing surface. In the new proposed designs, the asphalt wearing surface is very effective and can be used, and you do not have to fear the cracking between laminates.